Nice to see you guys, even though it's Zoom. We have a couple more minutes before I should start lecture. I have a question from Henry. Were they able to successfully redirect it? Well, yeah, I don't think the goal was to change, to deflect it. So in this case, because you're hitting a secondary, it was deflected. If it wasn't deflected, then it wouldn't have changed the binary orbit. So they're kind of using the fact that it's in a binary to make a more precise estimate of how much it was deflected. I think you could hit a single asteroid and then you would see a change in the orbital semi-major axis and eccentricity too, but it would take a really long time to detect it because you'd have to wait for it to drift over many months. To detect an orbit change, you have to have a long period of time. But because the system's in a binary, you don't have to wait that long. The binary period is only like 11 hours. So there's this extra step. They did deflect it, and the reason they know they've deflected is because it changed the binary orbital period. So it's kind of clever, like the fact that they picked a binary to do this deflection test in the binary system. Okay, it's 9:40, so probably ought to get back to class, or actually topics relevant to class. So first thing, yeah, I got hit by a car while biking to work on September 30th. I have a broken leg and a broken arm, so problems with mobility. So we're going to try Zoom out from now on, or for a couple weeks. We'll see how things go. I'm at home and the Wi-Fi connection can be kind of flaky sometimes, so it may drop out and then we'll just get back into it when it comes back up again. Usually it's only out for a few minutes, so stick with me if we have a Wi-Fi problem. What else? Oh yeah, so we didn't have workshops this week because of fall break, and but we had kind of a little snafu last week with Dan. Dan is a wonderful lecturer, but he didn't quite cover material for the problem set. So Thursday night, Rashad and I had this last minute, what do we do? So we just extended the deadline for the current problem set, which I think is number 5, right? And so it's due tomorrow. And so, but that might mean it'd be nice to have office hours today. So I wasn't sure how long I'd be functional. So I asked the TAs to step in, and so they have. So Rashad's going to do office hours right after lecture, and you can pick up problem sets from him. And then Moez is going to do office hours 3 to 5 in the POA. And Dan Watson, who enjoyed some of you guys coming by office hours last week, is opening his office hours henceforward to Physics 141 students. So I think his was 2 to 3:30. So this is all posted on Blackboard if you want to, figure out when these are. And so we'll take it from there. And then maybe next week I'll be back up office hours with Zoom or something. But this week I was like, let's see how it goes. So what other announcements? I think that's it. We have labs starting again on Monday. And I think that's all announcements, right? Okay, so on that note, let's look at what we're going to talk about today. So yeah, I'm used to lecturing at the Blackboard, so it's going to take a bit of adjustment here. Last week you guys heard about potential energy. In the classical setting, a particle, if it's under, a point particle with mass, it's under the influence of some force and has kinetic energy. It can have any value for the total energy, right? So in a classical setting, But in quantum mechanics, that's not true. So the word quantum means things are quantized. And in particular, energy is quantized. So the beginning of quantum mechanics, kind of like to quantize the most simplest thing, and that is light. So we're going to talk about the experiment that led people to conclude that light is quantized. So that's this wave-particle duality where everything has both wave-like properties and particle-like properties. So photons, it's not surprising that they have wave-like properties. So it's because they're predicted from Maxwell's equations. It's called electromagnetic radiation. It travels at the speed of light. But what's surprising was that energy had to come in packets. So whenever you have quantum mechanics, well, when you have a quantum mechanical situation when there's a particular fundamental constant that appears. So up to this time, we had, what are the fundamental constants we've talked about? Well, we had the gravitational constant, and we had the speed of light. So now we have a new one. It's called Planck's constant. And so here it is. It's 6.6 times 10 to the minus 34 joule second. So, so I put it in that units because when you multiply Planck's constant by frequencies in 1/time, then you get energy. And so since energy is quantized, you can see Planck's constant is going to come in when we start talking about quantization of energy. So, so the experiment that led to this interpretation of quantization of light that light comes in energy packets is this effect called the photoelectric effect. And Einstein was involved in interpreting it. And that's, in fact, what he won the Nobel Prize for. I mean, he's famous for a lot of things, but he won the Nobel Prize for interpreting the photoelectric effect. So, so what is the photoelectric effect? So, so what you do is you take a metal or something, you put it in a vacuum, and you shine light on it, and then you, put a voltage across the vacuum, and you try and detect electrons. So if the light, then you can vary the frequency of the light or the wavelength of the light, equivalently the wavelength of the light. So if the light is red, then you may not get any electrons. And then if you decrease the wavelength of the light, so it's like green in this case, then you might get electrons out, but they're not going to be very energetic electrons. And then if you increase you decrease the wavelength more, so in this case, blue light, then you get more energetic electrons. So, so for light, actually, maybe I should, well, in just a second, we'll summarize the photoelectric effect. So with light, and I'll go over this again, frequency is inversely proportional to wavelength. So a longer wavelength corresponds to a lower frequency. And so on the right here is plotted the frequency of the light versus the electron kinetic energy. So how fast are the electrons going that are liberated from this metal because there's light on it. And so when the light frequency is low, so that's the red light, you don't get any electrons. And then there's some critical value of the light frequency, you start getting electrons, but the ones that come out aren't very energetic. So the kinetic energy is really low. And as you increase the frequency of the light, which is the same as decreasing the wavelength, then the kinetic energy of the electrons gets higher and higher. So, so let's summarize what are the features of the photoelectric effect. So no electrons are liberated from the metal if the wavelength of the incident light is larger than a critical value. So, and the critical value depends on what material it is. So sodium is, has one free electron. And so when it's in a metal, it's pretty easy to kick off electrons, but other metals, the critical energy or the critical wavelength you need would be different. So yeah, critical wavelength or frequency value depends on the material. So the maximum energy of each liberated electron does not depend on the intensity of the light. So this picture, you can have a really bright light, even if it's red. So if a really bright red light, you don't get any electrons. And if you have a really bright blue light, you get electrons, but you don't affect the energy. You just get more of them, right? So it affects the number of electrons, but not their energy. And the maximum kinetic energy of the liberated electrons does depend on the wavelength of the incident light. So a weak violet light will only eject a few electrons, but they're going to be moving really fast. So, okay, so let's, see if I can get to my whiteboard. So let's review a little bit about light. So, so a photon, so what's a photon? Let's see, I need to move this like, all right. Okay, let's try this. Okay, photon is a light packet. So I'm going to write down the energy is h nu. So this is Planck's constant. And nu is the frequency. So, so when we say photon, we're actually referring to the fact that it's a single particle, has a certain energy with it. And so that's this light packet idea. So, so this is kind of the answer. Like when you interpret the photoelectric effect in terms of light packets, this is going to be the thing that helps you explain it. But let's look at frequency and wavelength too, and then well, look at how we can generalize what we had previously for relativistic particles, energy and momentum, and we'll look and see how photons fit into this. So, so a photon, so electromagnetic radiation moves at the speed of light. So this is speed of light. Kind of hard for me to write here, but. And so if we have a wavelength and we have a frequency, so recall that period is 1 over the frequency. And so if you have a wave-like thing, the time it takes to travel one wavelength is the period. And so what that tells you is the wavelength is equal to c divided by the frequency. And you can make sure you get this right. So a wavelength is in units of length. And the here, this is the speed, and that's length over time. And then frequency is 1 over time, so it cancels out. So yeah, so that so this is how you convert between wavelength and frequency. And when I keep saying longer wavelength corresponds to shorter frequency, this is, they're inversely proportional. Okay, so let's put this back into the energy equation. E. And so we have h nu, but now nu is c over lambda. Okay, so so if we want to, we can always write the energy in terms of wavelength instead of in terms of frequency. So okay, so now let's go back to our relativistic particles that we had previously. So before we defined for massive particles, we defined energy like this. And we defined momentum like this. So remember, gamma was the Lorentz factor, which looked like this, like that. So, so one thing that I didn't do when we talked about this was tell you about a thing called a relativistic invariant. And so I'm going to show that to you now. So relativistic invariant means, it's something that doesn't depend on what frame you're in. You compute it, you always get the same number. So if you're you can change the velocity of the observer and you'd still compute the same thing. So so let's compute this thing that looks like this. So it's e squared minus p squared c squared. And so I'm going to have both of these terms are going to have gamma squareds in them. And both of them are going to have m squareds in them, right? Let's just erase this then. M squared Okay, so then the E squared is going to give me a C to the fourth. And then this thing is going to give me a V squared, but then I have another C squared because of this thing, like this, which I can rewrite like this. Now I'm going to take the C to the fourth out, 1 minus V squared over C squared, right? So, but now take a look at what gamma is here. So gamma squared is 1 minus V squared over C squared. So this and this cancel. And so I can write this as M squared C to the fourth. So E squared minus P squared C squared is it doesn't depend on V at all. So it just depends on the rest mass. So we'll call this our relativistic invariant. Okay, so what if M is 0? So if M is 0, then E is equal to PC. And we can also say P is equal to E over C. And so that's going to be true for a photon. So we're going to take P is equal to E over C for a photon. So we don't have a mass for the photon, and it moves at the speed of light. But we want to be able to associate a momentum with it. So it makes sense to do it this way because it's consistent with our previous definitions for energy and momentum, but in this limit of not having mass or in the limit of having high velocity, meaning velocity goes to the speed of light. So, so I guess I can show that in another way. So supposing I take the limit of E over P as V goes to C. So we'll just put in the values. V goes to C of gamma M C squared. That's E gamma M V. So these gammas, so the gammas cancel, the M's cancel, and V goes to C, right? So this is equal to C. So, so what you find is that if you have a particle that's moving, a particle can't move at the speed of light unless it's massless. And if it's massless, then P is equal to E over C, okay? So, yeah, so that kind of tells you what photons. So let's to summarize, photons obey E equals H nu, and P is equal to E over C, right? Okay, so yeah. Okay, so let's take P now. And so remember for our photon, so E is H nu, so we'll put that in here. And then nu over C is equal to the wavelength. So I can write for a photon, P is equal to H over lambda. Yeah, so now we can turn this question around. You know, this particular formula, so let's just write it again. We could compute this for any particle. So let's invert it. Lambda is equal to H over P. So let's write this. So any particle has momentum, right? So what's the meaning of this wavelength if we just compute it? So you just take Planck's constant, divide by the momentum, and compute the wavelength. Is that wavelength interesting? So, so yeah, it turns out that wavelength is interesting. And in fact, it's called the de Broglie wavelength. So let's write it down. De Broglie is equal to H over P. And you can compute this for any particle. And so, so what de Broglie proposed was that particles like electrons, which have mass, would show wave-like properties. So this gives you a wavelength, right? So the wavelength of the particle, or the wavelength, would let you estimate where can you get diffraction effects or interference or something like that. And so he predicted that massive particles would show wave-like behavior, and this would let you estimate the size of the wavelength that would give you that wave-like behavior. And so after he did this, was like 1924. This was, so how do you do this experiment? Well, you want a big wavelength probably so you can detect it. So you just need slow electrons. Slow electrons means you need low momentum, and then lambda is big. And so this was then confirmed experimentally that you could get interference patterns with electrons and diffraction patterns. And this is kind of the heart of things like that make electron microscope work, for example, where you use the electrons themselves with their wavelength behavior. Okay, so let's go back now to explaining the photoelectric effect. Okay, so so the idea is, so when you think of the photons coming in and hitting the surface of a metal, the photons are now, they only have particular values for their total energy. And an electron that's sitting in the metal is bound to the metal. So, you can think of it as being in a potential well or being part of a bond. And so you need a certain amount of energy to kick that electron out of that potential well or to break that bond. So, so this critical energy that's set by the wavelength or frequency of the light is basically that value. It's this, how much energy do you need to liberate the electron? And so the energy of the photon, which is, we wrote this before like this, has to be greater than some energy E star, which we now interpret as how much energy you need to break it away from the surface. And so this explains why, if the wavelength is too long, you never get above this energy for the wave packet. And if its wavelength is shorter, then you do. And so if I write this instead as h nu, then you can see that it's proportional to the frequency. So what if you're above this critical frequency? So if you're above the critical, this critical energy or frequency or wavelength, whichever one you want to do, then you have more energy than you need to kick off the electron. And so the kinetic energy, how much energy do you have left after you kick it out? So you have the energy minus of the photon minus the binding energy. And so that'll be equal to the kinetic energy. And so this tells you why the kinetic energy is dependent upon the wavelength in this linear fashion, because you got this extra energy goes somewhere, it goes into the kinetic energy of the electrons. Okay, so I think that means I can stop the whiteboard, which you guys are probably going to be really happy about. And let's go back to the picture that we had here, where, so here's this picture of the photons kicking out the electrons, but here's this linear relation where the extra energy past the binding energy is going into the kinetic energy of the electron. Okay, so questions? Anybody have questions so far? Okay, so chime in if you want to say something, because we're all here. Okay, so let's move on. So we got some pictures here. So photons are quantized. The energies for photons are quantized now, but we have electrons sitting in potential wells of other sorts. So like a hydrogen atom is, it's got a proton and an electron, and they're bound electrostatically. And so what I'm showing you here is the 1/r potential for the electrostatic attraction force for a proton and an electron. And here we have a quantum mechanical effect in the sense that not all energy values are allowed you only have particular values or levels, energy levels allowed. And so these horizontal, so this picture, which shows you energy vertically, we have the potential energy. Classically, you could have any energy value, but quantum mechanically, you're only allowed certain energy values. And these horizontal bars show you the allowed energy values. So, so the hydrogen atom, so it takes, you see what theory gives you the allows you to predict these energy levels. So the equation, which turns out to be pretty effective, is Schrodinger's equation. So it's something you'll learn next term, how to solve it in spherical coordinates so that you can actually derive, find these energy levels. But what they obey is a 1 over n squared relation. So what's n? Well, n is an integer that tells you which energy level it is. So the ground state has n equal 1, and then the first, sometimes called the first excited state, has energy level index 2, 3, etc. And then it goes up to infinity, actually. So there's an infinite number, at least theoretically. And there's a particular energy for the ground state, which is 13.6 eV for hydrogen. And it's, different if you have a higher charge in the nucleus, for example, and a single electron, it would be a different value. So, okay, so we have quantized systems. So where do photons come in? Well, a photon is just an energy packet. And so if this atom changes state, so it starts off in E2 and then goes down to E1, that means it drops in energy, and a particular energy packet is emitted. And that specifies the wavelength of that light that's emitted. And so, so you get the photon that comes out. The wavelength depends on the energy difference of the two levels. So, so the Rydberg formula takes care of all the constants involved in here. And so the wavelength of the light that comes out depends on what's called the Rydberg constant, which is this R infinity thing, 1 over n2 squared, which is the it's the quantum number that it winds up in, minus 1 over n1 squared, which is the initial state. Or is it vice versa? In any case, you have to make sure it's positive to get the wavelength right. And this just comes from subtracting the values for the energy level. So remember, photons come from differences. Like you have to actually drop in energy to emit a photon. You can also go up in energy if the atom absorbs a photon. So if N2 is 1, that means it winds up in the ground state. Then it's called the Lyman series. And these tend to be in the UV. And if it's 2, then they're in the Balmer series. So let me show you what that means. Actually, so let's go down here. So here you can see if I start off there's a whole consecutive possibilities, and then I wound up in the ground state. That's a pretty big jump. And so those wavelengths are pretty short, or the frequencies are high. So that's why they're in the UV, because the photons have more energy because there's a bigger jump involved. The Balmer series, you have dropping to the second the first excited state, or the second energy level. And there's not as big an energy jump. And some of those are in the optical wavelengths. And then as you get to the Paschen series and the bracket series, the Paschen series goes to the third state, and the bracket series goes to the fourth state. These tend to be in the infrared. So, which is just telling you that the wavelengths are even longer, the frequencies are even shorter. So there's less energy involved in the transitions. So let me show you this. So this is like the difference between absorbing and emitting. So, if you're in an excited state, so like here, the E3, you drop down to E1, then the energy of the photon is the difference in the energy levels, and that photon is emitted because the hydrogen atom is dropping in energy. And that is part of the Lyman series. It would be the second one in the Lyman series. In this case, supposing you were in the E2 state, you jumped up to the E4 state, you would absorb energy. So you would absorb a photon to get kicked up into a more excited state. And that one would be you'd absorb a photon that's a Balmer, one of the Balmer transitions, because starts off in E2, right? So what if I have more energy than in the exact energy to jump between two states? So for example, this photon, if I started in E2 and I absorbed a photon that was above, that gave me above this, 0 here, you would free you would actually ionize the atom. You could free the electron. And just like we saw with the photoelectric effect, you have extra energy to unbind it. And so it comes out with kinetic energy, some more kinetic energy. And it can have any value, because kinetic energy can have any value. So there's nothing quantized about a kinetic energy. So because that's true, so when you go from one level to another level, that's called line or bound transitions. And so you get particular lines. But if you go from a line to a continuum state, which would be like a free electron, which could have any value, that's a bound free transition. So, and those can, have a range of values. And you see that in spectra, actually, where you might see a big, to the left of some wavelength, like Lyman alpha, you'll see photons, and all of a sudden there's a big absorption band. So because all the electrons or all the photons are absorbed past some frequency. So you do see that as a continuum process in spectra. Okay, so let's go to the next picture here. We talked about this. So yeah, the differences between absorption and emission. So when would what type of spectra give you absorption and emission? So if you have a really bright source, like suppose it's like a sun, and you put cold molecular hydrogen in front of it, that means all the atoms are in the ground state, but the thing behind it has all possible wavelengths of photons. And so the cold gas can can absorb those photons. And that's why you'll see an absorption spectrum. So you have cold gas in front of a continuum source, you'll see a spectrum that looks like that. On the opposite viewpoint, supposing you have a hot gas and things are jumping down into lower energy states, then you'll see an emission spectrum. So something that looks like that. So like ionized, so whenever you have an ionized region in the near their hot stars that are ionized, so you'd say, well, if it's ionized, it's all hydrogen atoms, the protons and electrons, but they do have probability to recombine, and then they're pretty hot. And so ionized regions tend to be pretty bright in emission lines, typical of atomic hydrogen. So yeah, you detect H alpha and H beta from outer space. It's pretty bright, particularly in the optical. So these are optical spectra. And then, so when you look at this, so one of the amazing things about quantum mechanics is being able to predict this spectrum. So you see a bunch of lines, and it's like, what's the pattern, or what's the theory that gives you these lines? And so quantum mechanics is that theory. And when you guys learn about quantum mechanics, you'll learn to predict the spectra of things like hydrogen. So helium has a different spectra. I don't know much about helium, but here's an example. So so how do you know when I talk about absorption, you need cold gas in front of a continuum spectrum, you'll see absorption lines. So in order to see a particular transition, the system has to be in the initial state for that transition. So for example, on the left, if I have a low temperature gas, I'm never going to see any transitions involving these upper levels because the system's not in it. So I could see, it could absorb a photon from the ground state and go up to an upper level. There might be a few atoms in E2, and then I'd see an emission coming down. But mainly a cold gas, you're only going to see absorption because almost everything's in the ground state. But if you have a higher temperature, then more of these higher energy levels are going to be populated. And so you'll see transitions between the other level states. So you'll see emission going down here and emission going down here because things start off in these higher energy levels. So, so that means when you take a spectrum of an object, or some kind of emitting gas in a young stellar object or something, when you look at the line ratios, So that means you're comparing how bright is it in the E2 to E3 transition compared to the E2 to E1 transition. What that's telling you is about the fraction of atoms that are in these different states. And that's sensitive to the temperature. So you can learn about the temperature from looking at the brightness ratios of different emission lines. Okay, so that's the hydrogen atom. Now we'll talk about other systems. So we talked about, well, Dan should have talked about harmonic oscillator potential energy. And so you guys should know that the potential energy for a harmonic oscillator is 1/2 kx squared, where k is the spring constant. And so we can again draw the potential energy, this U-shaped thing. And again, now the energy levels can't be anything. Classically, they could be anything. But when the system is quantized, it only has particular values. And for the harmonic oscillator, it's actually really special. The energy levels are all equally spaced. It's like a ladder spectrum. And so I've shown you here that the ground state is actually at, ground state is actually at h bar omega over 2. So I haven't told you what h bar is yet, but h bar is just h over 2 pi. So convention is to use that and to put it in terms of the angular frequency instead of into terms of nu, which is the actual frequency. And then each state is just separated by h bar omega. So let me just write that down for you here. All right, I did write it down. Let me just show you what I'm saying here. So h bar is h over 2 pi, and h nu is equal to h bar omega, right? Because omega is 2 pi nu, right? So the angular frequency is 2 pi times the actual frequency. So you can write h nu is equal to h bar omega. So you might wonder, why are people doing this? But it's just convention that people use h bar often in quantum mechanics instead of h. Doing order of magnitude stuff, often people will use h. But when talking about harmonic oscillators, h bar, everybody always uses h bar. So the energy levels are actually given by this. So you have h bar omega 0, where omega 0 is set by the spring constant and the mass. And then n is the quantum number, which ranges, in this case, it ranges from 0 to infinity. So, it's just it's an integer, just like we had for the hydrogen atom. So, so if we actually had a harmonic oscillator where you had one end of a spring fixed and a mass connected with a spring, so if you could achieve that, and actually you probably can, with a quantum dot or something. In any case, then the frequency is just square root of k over m, this omega 0 thing. Just like we talked about classically last week. If we have a free molecule with 2 atoms, N1 and M2, then the frequency is square root of k over mu, and mu is the reduced mass. And we'll derive this next week when we talk about center of mass and motion with respect to the center of mass and relative motion. So this actually characterizes the relative motion. And so that's how you compute the frequency for a molecule. So let me show you that. So up here, I have this little picture of a molecule, right? But the harmonic oscillator down at the bottom here, this at the bottom here is like a harmonic oscillator, but this spring may dissolve eventually for an actual molecule. And so an actual molecule, it may become free if you pull it apart enough. And so modeling it with a harmonic oscillator is probably a good approximation at the bottom, but the potential energy may curve over as you pull it further and further apart. So the bond strength may not be completely linear proportional, and then the energy levels get closer together and it can become unbound. Right? So this is maybe a more realistic approximation for an actual molecule. But when you talk about a molecular bond as if it were a spring, I mean, that's the degree of freedom where the 2 particles can change the distance between them. And so that's the vibrational degree of freedom for a molecule. So any case, so yeah, so that gives you the spectrum of a quantized harmonic oscillator. So moving on. So a molecule has other degrees of freedom that it can move. So instead of just changing the distance apart between the two atoms, you can also rotate. And so if it's rotating faster, it would have more rotational energy. The rotational energy is also quantized. And so this is called a quantum rotor. And the spectrum for that also depends on quantum numbers. And here, L, I think, has to be greater than 0. So there's probably a mistake there. L should be greater than 0, not greater or equal to 0. I'll fix that. In any case, so this is what the spectrum looks like. It depends on h bar, and it depends on I, which is the moment of inertia, because the spin is involved here. And for this type of motion, you assume that the distance between the two atoms is not changing. So let's look at this formula a little bit. So let's compute what would happen if I did a transition between two consecutive energy levels. So these are the energy levels indexed by the quantum number. So if I do a transition from L to L minus 1, which means just dropping down to the next consecutive level, so I can put in the formula. So it's L times L plus 1 minus L minus 1 times L. So that's just one lower in both cases. You subtract these, you get h bar squared L over I. And so that tells you that the distance between the difference in energy between the consecutive states increases the higher L is. And so I've drawn this here in this picture where you can see at the beginning, going from 1 to 2, delta E is just h bar squared over I, where I just have L equals 1 there. And then it's 2 delta E, and then 3 delta E, 4 delta E, 5 delta E. So, so it's a different type, it's a different shape, or different, the spectrum. So like the harmonic oscillator was like this ladder shape, but the quantum rotor, the distances between the energy levels gets bigger and bigger as you go up. And the hydrogen atom was the opposite. They got closer and closer together as you went to higher energy levels. So it's different phenomenology depending upon the setting. So so moving on, yeah. So molecules, they have these different degrees of freedom. So, well, why can't you have both vibrational transitions and rotational transitions? And you can. So the vibrational, the distance in energy for the vibrational part tends to be much bigger than the distance between the energy levels for the rotational part. And so I can show you that here. So here's a rotational set, and then here's another rotational set, and they're separated by the vibrational energy distance. So the vibrational stuff is a ladder, so there's equal spacing because it's like a harmonic oscillator. Where the rotational stuff has this, increasing distance between them. So you could have rotational transitions where you go between these consecutive rotation states at a particular vibrational state, or you can have vibrational transitions where you would stay in the same rotational state and you just drop down by the vibrational energy level, or you could have combinations where you change both the vibrational and the rotational energy index by quantum number. So really, when you write a picture like this, you have the total energy depends on two indices, the vibrational and the rotational one. And so you can have transitions between both. And there's various selection rules that tell you that sometimes they aren't allowed or they aren't allowed. They are allowed. So since the rotational ones are really small, they small jumps in energy, they tend to be in longer wavelengths. So you tend to see them in submillimeter, for example, in the radio, almost the radio. And the vibrational ones tend to be infrared more. And because there's a lot of possibilities, you have like lots and lots of energy levels to go between, there are a lot of possible transitions. So you tend to see whole bands. And this is one of the reasons our atmosphere is pretty opaque in the infrared, is there's a lot of energy levels so that the molecules can can undergo transitions, and that means they can really absorb photons very thoroughly in the infrared and all the way out to the submillimeter. So it's hard to look through the atmosphere. It's also interesting. So here I'm doing a really simple model, but of course molecules can have more than 2 atoms. So rotational rotational spectra can be pretty detailed and complicated. There's a whole field predicting and trying to understand rotational row vibrational transitions in molecules. And whole bands of absorption in the atmosphere. Okay, so I mostly talked about line emission and absorption processes. So we did talk about one continuum process. And the one continuum process I mentioned was bound-free transitions, where you go from in the hydrogen atom, where you go high enough past that you unbind the electron, and then it's a free electron. So that's bound-free emission or absorption. There are all other types of continuum radiation processes. So like synchrotron radiation, where you have electrons are accelerated because of magnetic fields, so they can, do these little spirals. And because they're accelerating, they emit. Bremsstrahlung emission is when electrons, or not just electrons, ions are decelerated against each other. There's collisions, and that involves, because they're free particles, there are a lot of possible, there's no quantization involved. So that's a continuum process. And inverse Comptons. Yeah, what's inverse Compton? So Compton emission, or inverse Compton emission, depending upon whether you upscatter or downscatter. So that's when you have photons and they are passing through a gas, and a photon can scatter off of a particle and gain energy or lose energy from the particle. And so, for example, in the universe, there's this microwave background radiation. And if you happen to have a hot gas in front of it, you can upscatter the cosmic microwave background radiation and make them more energetic, because they scatter off the hot gas. So that's called inverse Compton, because it actually increases the energy in the photons. So you need both photons and a gas, but that too is a continuum process. So not involving quantization, but just put these different things in perspective. Okay, yeah, so last thing to talk about in quantization, we'll just mention quickly what a laser is. So why are we mentoring lasers? So they involve quantized energy levels. And so let's throw it in this section. It's like, so what's a laser really roughly? So what you do is you start off with some system that has a couple of energy levels. And so you have a ground state and a high energy state and some intermediate state. And then you shine light on it to try and pump it up to this high energy state. And so the system now try and get things out of the ground state, absorb a bunch of photons. So you have a bunch of things sitting up here. Then once they're in that high energy state, they can emit and drop to this intermediate level. And so the goal is to get a whole bunch of atoms in this intermediate state. And then you try and have them all in this cavity. So if one of them's sitting there in the intermediate state and a photon passes by, it's much more likely to emit than just spontaneously. And so this is called stimulated emission. And when that happens, the emission is actually in phase. And so to show that here, so you've got this excited atom and this photon coming by that's exactly at the right energy, matching the energy between the intermediate state and the ground state. And what you get out, so the excited atom drops into the ground state, and you get 2 photons out, and they're the same energy and the same in phase with one another. They also have the same polarization. So then you put the whole thing in a cavity, and the reason you put it in the cavity is because you want the photons to bounce around and excite more transitions. So you get more and more transitions building up. And then you make a very slightly leaky mirror on one side, so some of it can get out. So the idea is, because you keep pumping the system so that you always have a source of these things in the intermediate state, you keep producing photons from stimulated photons all in phase together. So that's supposed to be what a laser is about. Okay, so let's summarize. So this section, photons come in quantized quantities. So these are like particular energy packets, and that is set by the frequency of the photon. So the energy of a photon is either h nu or h bar omega. You can write it either way. And h is Planck's constant. So this is the first time we're seeing Planck's constant. Nu is frequency. And for a photon, the wavelength lambda is c over nu. Photon momentum, P is equal to E over C, which you can also write as H over lambda. And this we showed was consistent with our previous definition for relativistic particles, but for massless particles. So our previous definition, we didn't give any form for a massless particle. And then this extends our definition for energy and momentum to cover massless particles, so photons. Yeah, so that's nice. So what else did I want to say about this? Oh yeah, so so looking at energy packets. So when you look at E energy is h nu. So if I go into the radio where frequencies are not very big, so photons are just really low energy. So you just get a ton of photons. And then compare that to going into the X-rays or the gamma rays, where you need a ton of energy to get a single photon. So this then kind of informs you about detection strategies. So in the radio, people tend to do interferometry, where you use the fact that you've got tons of like not very energetic photons around, but you can get a lot of information from them by taking into account the fact that you've got lots of them. Whereas in the gamma rays, you're basically looking at light buckets, because every photon is precious. You only get like one or a couple, and every one is significant. And so you contrast that light detection strategies, there's a transition somewhere in the infrared where both techniques become kind of viable, where people do interferometry in the optical and the infrared with quite a lot of work. Or you can just have light buckets where you're just collecting energy, what people call light buckets. So like bolometers, which just measure how hot things get from looking at, collecting light. Yeah, so that's kind of the last thing to keep in mind. So because photons, there's a relationship between the momentum of a photon and its wavelength. You can compute this thing called the de Broglie wavelength, but for things that aren't photons. And that's just for any particle, it's Planck's constant divided by momentum. And for a massive particle, and that tells you, if you compute that tells you the wavelength of that, how it gives you an idea of how that particle is going to behave as a wave-like entity, right? Not just as a particle packet-like entity. So energy levels are quantized often. And emitted or absorbed photon energies are equal to the difference between energy levels. So that's something to keep in mind. It's kind of a detective work. Like if you're trying to understand something and you get a spectrum, so how do I explain that spectrum? So the grand age of atomic and molecular physics, there's still ongoing lots of studies trying to understand these complicated systems. And to this date, there are still spectral features that are not identified. In the solar spectrum there are, and also in the interstellar medium, there are spectral lines where people don't really know what's causing them. So they could be really complicated molecules. So that's still ongoing, where you're trying to make predictions or try to make models to explain spectra. Yeah. So energy levels of a quantized harmonic oscillator are evenly spaced and separated by h bar omega, where omega is square root of k over m, and that would be for, you know, a regular harmonic oscillator, but it would be square root of k over mu if you had a molecule with 2 atoms in it, and mu is the reduced mass. And in this case, yeah, so this is the way the energy levels are written in terms of quantum number L. And in this case, L does go from 0, start at 0. So for a quantum rotator, this is what the energy levels look like. And in this case, L is positive integer, starts at 1. And together, vibrational and rotational energy levels and transitions make up the rho vibrational spectral molecules. That's the idea. Okay, so that's the end of this part of this lecture. Any questions? Y'all are quiet. No questions? Okay. We have one chat. Oh, what's an example of a real-life quantized harmonic oscillator? Well, molecules, you know, I mean, when you look at the vibrational spectra, they are actually harmonic oscillators. So that's an example. But you could have maybe an atom that's like very weakly bound to something that would also act like a vibration, you know, act like a harmonic oscillator possibly. You probably need to ask somebody who does more work, and I'm not sure what setting actually. There's probably a setting where there's a really good approximation. For the quantum computing, they really don't want evenly spaced. They want things not to be evenly spaced because, so when you look at actually I should mention that. Let's go back to the harmonic oscillator again. So what are the transitions? So I could go from here to here and I'd get a transition that's h bar omega, or I could go from here to here. Or actually, let's go down because then it would be a emission process. So jumping from here to here is the same energy as jumping from here to here, is the same energy as jumping from here to here. So I could also, so one of the spectrum has h bar omega, but then I could jump 2, and then it's 2 h bar omega. But you don't really know when you see the transition, and supposing I'm looking at what photons come out, I see h bar omega. I don't know which levels it transitioned between, because there are a lot of possibilities. It could go from 5 to 4 or 4 to 3 or 3 to 2, right? So you don't have a lot of control or information because there's a degeneracy, you know, the spacing's too even. Whereas if you go down to this setting, you know, if I go from here to here, it's 5, but if I go from here to there, it's 9. If I go from here to here, it's 7. And so you have a lot more information about which levels it went, what level did it originate from, and what level did it wind up in. So in quantum computing, you want to have control about which levels it's going into. And so you really don't want something that looks like a harmonic oscillator. You want something that has unique transitions. So I know that is an issue in design. Any other questions? Okay, we have a few more minutes. So I am going to now move on because we've got more material to cover. Okay, so let's look at the weight pad again. Okay, so our next topic is we're going to talk about the center of mass.
I think people asked some more questions in the chat.
Oh, we do. Oh, thanks for letting me know. Why does the de Broglie relation not have a Lorentz factor for momentum? Well, it can, right? Because all it depends on is the momentum. So you can put whatever you want in there. So if you have a particle, a massive particle, then we know what momentum is. It's gamma mv, right? And so you just insert that if you want the Lorentz factor. So, and what does h bar mean again? H bar is just h over 2 pi. It's just a handy thing. you wonder why bother with a new symbol here? But you're going to see it so many times written like that. So I'm just introducing it to you now. You'll see H bar all over the place. Also a special text symbol, which is another way of letting you know that physicists just use it all the time. So yeah, that's what H bar is. It's just shorthand. Any other questions? Okay, a few more minutes here. So let's talk about the center of mass. So how about a new color? Why not? Green. So let's put, we have M1 and we'll have a second mass M2. So we'll put M1 here and we'll put M2 here. And M1, we're going to put it at position X1, which could be a vector, but right now we're really just going to, do things on a line. And then we have a position X2. And then, so you can see I've drawn this with this guy, M1 being larger than M2. And so the center of mass, which is, weighting the position by the masses, is going to be somewhere like in here. So that's the center of mass. So let's define the center of mass for this two particle system. So I'm on the x-axis here like this, but I could just do this in terms of vectors. So in fact, I did that in my notes. So we'll define a position, the center of mass position, which is weighting these positions, so x1, by their masses. Now I need to divide by the total mass because it's like the sum of the weights. So that's the definition. So I can make this, that's the definition. So I could take the derivative of this expression with time. So let's do that. So I can just take the time derivative. So the masses aren't changing. So the velocity of the center of mass. So let's just take the time derivative of this. So dx1 dt is v1, right? So it's going to be m1 v1 plus m2 v2 over the sum of masses. So, and that's the velocity of the center of mass. Okay, so now we're going to do some manipulation. So actually, so let me go back. How do I go back? There we go. So what I'm curious about, what I'm going to compute is this distance. And so we have a distance between the two. Let's think, what is the distance between these two particles? So since this one is, M1 is at X1 and M2 is at X2, the distance between, whoops. Wait, I have a question. How to derive the equation of the center of mass. So I'm defining it. I'm not deriving it. I'm defining it. And yeah, it's a definition. So it's the position weighted by mass. Okay, so back to what I was saying here. What's the distance between the two particles? So the distance between the two particles looks like this. So I just take the vector between them and I take the magnitude. Well, what I want to compute is the distance of x1 from the center of mass. So for many systems, it's really helpful to talk about, so we have two particles. I could track the position of each particle, but often you can solve the problem much quicker if you decompose it into center of mass motion and the relative motion. And then sometimes, often the center of mass might be either drifting at a constant rate or it's fixed or something. And then to observe it, you want to know what's the position of one particle with respect to the center of mass, because that's what you're going to see from really far away. So an example is like, if I'm looking at a star with a planet around it, and because the planet's going around the star is moving very slightly. Center of mass is not at the position of the star, it's very slightly off. And so what you're interested in is how far away that star is from the center of mass of the system. That's what you're going to see. So this thing right here is what I want to compute. So I'm going to compute that now. So with a little bit of manipulation. So what is that position? We have the center of mass. Let me get rid of this, it's in the way, right? Okay. So we have the center of mass position, and I'm going to subtract off the position of x1, and this is what I want to compute. So I'm going to insert the formula for the center of mass. Over m1 plus m2 minus x1. And now I'm just going to multiply by both sides, top and bottom, by this, like that. And we'll do some regrouping here. So I have a m1 x1 and m1 x1, those are going to go away. And then I have an m2 x2, that's this term. And then I have a minus x1 m2 over m1 plus m2. And this I can rewrite in a more simple way. X2 minus x1. Okay. So going back to this picture, this distance, which is, this is m1 and that's m2. This distance is equal to the ratio m2 over m1 plus m2 times the distance between. So this is a really handy formula. It's going to be really handy for next week's problem set. So I could, so I did m1 here. I computed this distance. But what about this distance? Like, suppose I want to know the distance of m2 from the center of mass. Well, it's pretty easy to figure that out. You just reverse all the indices of everything. And so we got x center of mass minus x2 is equal to m1 over m1 plus m2, x1 minus x2. There might be a sign difference, which kind of makes sense if you want to keep track of the sign difference. If you're only doing distances, you don't have to worry about the sign. So, that's straightforward. Okay, so let's do a quick example. So again, we're going to go, we have m2, m1 here. And we have m2. And now I'm just going to talk about things in terms of d. Here's the center of mass. m2. And supposing I start off with a system like this, and I know this distance. And so this distance, we wrote down the formula for it before. It's x1 minus x center of mass is equal to m2 over m1 plus m2 times d. So supposing I shrink the distance between the two particles, and I want to know how much does that affect the distance of m1 from the center of mass. Well, so this formula tells you the answer. So what's the change? So supposing those two particles just kind of like, they decided to get closer together. They like exerted a force, equal and opposite force on each other so that they got closer together. Then how much does m1 move? So supposing d shrinks to d over 2, how far does x1 move? So that's the question. So we're going to assume the center of mass doesn't move. So it's like they're both sitting on the sliding tabletop. They're just like pulling each other together. And you want to know how far did m1 move. So this formula tells you that. So the initial distance is just this. So the initial is x1 minus x center of mass is equal to m2 over m1 plus m2 times d. And the final distance is, so I'm just shrinking it by 2, d over 2. And now I just subtract them. And so the change, whoops, so erase that, change. So I just want to subtract these two, is m2 over m1 plus m2, d minus d over 2, which is equal to m2 over m1 plus m2 times d over 2. So let's call that delta or something. So that's the answer. So next week's problem set, you'll see this type of problem. It'll be like, there's a dog on a boat and the dog moves a certain amount, then how far does the boat move with respect to somebody looking on the shore? So this is this type of problem. You'll be using exactly this formula to answer those questions. Okay, so let's move on a little bit. How much time do we have? Oh, we have a few more minutes. Okay, good. Okay, so that was for 2 masses. So let's now, what if we have n masses? What's the center of mass? So I'm just going to define it again. So first, let's figure out what the total mass is. So we have mi, that's the mass of each particle, and we have xi, that's the position of each particle. So the position of the center of mass is going to be the sum over I equals 1 to n of mi xi divided by the sum of all the weights. So that's the definition. And this is a vector. So this thing on the bottom, you can recognize just the total mass. Like that. So we could write this thing like this. Over m total. Like that. So that's if you have n masses. What if I have a mass distribution? So that's a little bit different. So what's a mass distribution? So mass distribution we would characterize with a density distribution. So we have a density as a function of position. So first, let's figure out what the total mass is for this thing. So we have distribution of density, the total mass. We will integrate up the density. And, overall volume. And, you'd integrate it, if it was like a solid body, you'd integrate over the region, but you could have a density variations. So, you can, that would set the boundaries of the integral. So that's the total mass. So the center of mass, then, we're going to weight the position. So there's a bunch of ways to write this. So I can just take x as a vector. And now I divide by m, which is the total. So let's be specific about what we mean here. So if I have x center of mass is, let's write it out as a vector. X center of mass, y center of mass, z center of mass. Then x center of mass would be 1 over m, x rho of x, y, z, dx, dy, dz, like that. And then you could do this for y, you could do this for z, and so that would give you each coordinate separately. So that's how you do a mass distribution. So there's nothing really different between this mass distribution and the end points. So you just have to think a density is like a little bit of mass at a particular position. And so, you know, the two are basically equivalent, just that we write them with, you know, integral sign instead of a sum. Okay, so how are we doing on time? And I think that's probably a good time to stop. Do we have any more questions? See if I can get out of this. Stop share. Questions? In any case, that was kind of a new type of lecture for me. Hopefully I'll get better at this, and hopefully I'll get better and actually can get onto campus. We'll see. In any case, I will post lecture, even though it's going to be kind of embarrassing, but I'll post lecture, and I look forward to seeing everybody in the same format on Tuesday. And we'll talk more about center of mass. And then we'll talk about multiple particle systems and work done on multiple particle systems. And what else are we going to talk about? Conservation of momentum and thrust and energy of multiple particle systems. So we're generalizing now from one particle to many particles. So that's where we're going. So if there are no more questions, then we're just going to end. Signing off then.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.